Building open data lakes on AWS. In the following demonstration, we will build a simple open data lake on AWS using a combination of open source software, including Debezium, Apache Kafka, Kafka Connect, Apache Hive, Apache Spark, and Apache Hudi in Hudi DeltaStreamer. First, we will explore the question, why do organizations want to build a data lake? Next, we will look at one possible data lake architecture and highlight the technologies that compose the solution and how those technologies work together to form an end-to-end data pipeline. We will briefly discuss the data set used in the demonstration. And lastly, we will spend a majority of our time seeing how these technologies can work together to form an effective data pipeline, moving data from a data source to our data lake, and then preparing that data for analytics and machine learning. Why data lakes? In my experience, many organizations that are considered building a data lake are trying to solve a common challenge. How do they extract data from multiple disparate data sources, CRM systems, HRIS systems, relational, non-relational databases, and third-party data feeds? And how do they store that data in a single, secure location where data analysts and data scientists can perform federated analytics and machine learning across the different data sets? We will employ several open source technologies running on AWS using AWS managed services to move data from a data source to a common secure location, our data lake. First, let's see how these technologies fit together to accomplish our goal of moving data from a PostgreSQL database into our data lake. First, we have our data source, a PostgreSQL database. The database has data that is slowly changing over time. We need to make sure that the existing data, as well as any future inserts, updates, and deletes, are reflected in the data lake. Next, using a combination of Apache Kafka, Kafka Connect, Apache Registry, and a Kafka Connect source connector that leverages Debezium, we will continuously move data from the database into Apache Kafka. The changes will be stored in Avro format in Kafka. The schema for the Avro format messages will be stored in Apache Registry. Next, we'll use a similar combination of Apache Kafka, Kafka Connect, Apache Registry, and Kafka Connect Sync Connector that leverages several Confluent S3 storage dependencies to continuously move the data from Kafka to Amazon S3, keeping it in Avro format. Steps 2 and 3 are collectively known as Change Data Capture, or CDC. Specifically, we are using log-based CDC to continuously move data from our database's logs into our data lake. The Avro format data in S3 is still considered raw. To transform that raw data into a file format and structure that's more efficient for analytics and machine learning, we'll use a combination of Apache Spark and Apache Hudi with Hudi's DeltaStreamer. DeltaStreamer, running as a Spark job, will continuously transform and move the raw data into a refined data set and manage those changes to the data set as changes are made in our PostgreSQL database. By continuously executing steps 2, 3, and 4, our data analysts and data scientists will have access to a refined data set that they can work with securely in our data lake. Moving from left to right, our PostgreSQL database will be running on Amazon RDS. Our Apache Kafka cluster will be running on Amazon MSK. Apache Registry, Kafka Connect, Debezium, and the Confluent dependencies will all be hosted on Amazon EKS, managed Kubernetes. DeltaStreamer, Apache Hudi, Apache Spark, and Apache Hive will all be running on Amazon EMR. The backing store for Apache Hive, a MySQL database, will be running on Amazon RDS. Finally, all of our data, the files, Apache Avro and Apache Parquet files, and our configuration files will all be hosted in Amazon S3. The source of the data, or the dataset, that we will be using in our demo comes from Kaggle. We will be using the Museum of Modern Art Collection, or MoMA collection. The dataset consists of 2 CSV format files, artists and artworks. The artists CSV file contains approximately 15,000 unique artists. The artworks CSV file contains approximately 122,000 unique pieces of artwork with a title. To get started, I have downloaded both CSV files and imported them into the PostgreSQL database. I will now move into the demonstration, walking through each step as described in the architecture overview and how each of those steps fit together to create an end-to-end data pipeline. So I've removed all previous artifacts from a fresh copy of Apache Registry. Schemas in Apache Registry are referred to as artifacts. Currently, my copy of Apache Registry has no artifacts. The schemas, aka artifacts, will be created by Kafka Connect, the Kafka Connect source connector, and Debezium when we start the demonstration. So again, Apache Registry is running on Amazon EKS or managed Kubernetes. So within a pod, I have a container running Apache Registry. And once we get started, I'll flip back to here and I'll show you the schemas that are going to be created by Debezium. A few other things, my EMR cluster that I have running, I have a Jupyter notebook running, Apache Spark Jupyter notebooks. We're going to run a few commands in that, and I'll walk through those commands in a few minutes. Also, Amazon S3, again, let me just touch upon that. I have a Open Data Lakes demo US East 1 bucket. And the only thing I have in this bucket right now, and this is going to be our data lake, I've also put my configuration files in there for Hudi. Once DeltaStreamer starts running, DeltaStreamer will pick up some property files from this bucket. So I'm going to use this for both my configuration and for my data lake, this S3 bucket. Flipping over to the command line for a minute, I have a few different pods running. I mentioned on Managed Kubernetes Service, that's where we're going to be running Apache Registry. I also have Kafka Connect running. So we can log into Kafka Connect. Let me log into that container. So I'm logged into the Kafka Connect container. This is where we're going to start Kafka Connect in a minute, and then install our source and sync connectors. I've also logged in a separate terminal window into Amazon EMR. This is where we're going to be running DeltaStreamer from. So once again, if you recall our diagram, Kafka Connect, the source connector, is going to move the data from Postgres into Kafka, and then the sync connector is going to move the data from Kafka into our data lake, into an area of the data lake which contains raw Avro data. Then DeltaStreamer will take over, will move that raw Avro data into a refined part of our data lake in Parquet format. Let's get started. The first thing we're going to do is we want to start Kafka Connect. So I have all of my commands ready to go. I'll walk through those as I do them one at a time. So I've already copied the files over. We've deleted any previous topics in Kafka. So let me first start Kafka Connect in the background. And we can just tail that log and we can see that Kafka Connect is starting up. So I'll let Kafka Connect start up fully. Now, when Kafka Connect starts, it will not have any sync or source connectors loaded. We'll have to go ahead and load those ourselves. So I'll just give this a minute or two to get started. Okay, so it looks like Kafka Connect is started to a point. Let me clear that. The next thing we want to do is install our sync and source connectors into Kafka Connect. Let me grab the two put commands. These are the commands that will deploy our source and sync connectors. And I'll just show you over here, I have a config folder, and we can see that I have a number of configuration files, property files. I also have a few different source and sync connectors. If you've read any of my previous posts, I've written a number of posts on working with Debezium, Kafka Connect, a few technologies. These are all the configuration files. In particular, the ones that we're going to be working with today are this Debezium Avro source connector, Postgres MoMA, so our MoMA database. And I also have an S3 sync connector, Debezium Avro MoMA. So this is my source connector, and this is my sync connector, and those are the ones that we're going to be running today. Go back here and grab my commands. And we can see that both of those started up. So let me clear that. I'm going to go back and first off, we can list the connectors that are running in Kafka Connect. So that's a good sign. We see that both our source and sync connector are running. I want to see if they're deployed, but are they running? So did they start successfully? We could look at the logs. We can also run another git command for each one, so I'll do those one at a time. We can see here that this is our source connector, and it is in fact running, so that's a positive sign. And let's check our sync connector to see if it's running. Again, just another git command, and it looks like that's also running, so both our source and sync connector are running. If they're running, what does that mean? That means that our source connector using Kafka Connect and Debezium has pulled the artist files from the Postgres database and put those into Kafka. So for every record in our artist table, which is also in the logs, and this is log-based CDC, so Debezium is reading the logs from PostgreSQL. Each one of those entries are written to Kafka, and we're gonna check that in a minute, and I'll show you how to check that. In addition, because we've loaded our sync connector, the messages in Kafka have been picked up by the sync connector, and those have been written to Amazon S3 in Avro format. So we should be able to look at our topic and see some messages in our topic. We should also be able to look at our S3 bucket, the raw area of our data lake, and see some Avro messages in there for the artist topic. So first off, I'll switch over to S3 and we'll take a look. You remember that we just had our configuration file here. If I refresh, you can see there's a topics folder now. Now I'm only interested, for the sake of brevity for this demonstration, I'm only going to look at the artist. We could just as easily have the artist and the artwork, and we would see multiple files. So we would see moma.public.artist and moma.public.artwork. Again, just for the sake of brevity for this demonstration, we're only going to focus on the artist right now. And we can see here we have a partition 0, so the data is not partitioned. So you get that partition 0 automatically, but you can see that we have a series of Avro files. And if you look at the numbers, that would indicate that there's about 300 artists in each one of these files. So as I scroll through these, you recall we had about 15,000, a little over 15,000 artists. There is an Avro file, again, 15,000. You have about 51 files, so about 300 artists per file. Those have been written into our data lake, into Amazon S3, into a directory or key called topics. And then for each table that we examine, in this case we only examined the MoMA database public schema artists table, there was a topic written that's also reflected in S3. So we can also look at Kafka and take a look at that topic. So let me switch back to PyCharm and grab a few more commands. So first let's just list our topics. So I'm going to switch back to I'll clear this out. So again, I'm in my Amazon EKS Kubernetes pod container running Kafka Connect. And this is also running the Kafka API, so we can do a list on the topics. I cleared out all the topics that were running previously, so we don't have a lot of extra topics here. But you can see 4 key topics. 3 of those are for Kafka Connect. So again, before starting this demo, I deleted any existing topics. When I started Kafka Connect, these 3 topics were created, and these are used by Kafka Connect for configuration, tracking its status, tracking the offsets of the brokers. And you can see here another topic, moma.public.artist. So again, MoMA database, public schema, artist table. Had we pointed maybe just to a schema with multiple tables, we would have seen multiple topics, 1 per table. In this case, we're only looking at artists, so we only see the artist topic. Let me just look at the first 10 messages. So again, if you're familiar with Kafka and using the Kafka APIs, I'm using the Kafka console consumer. I am looking at the moma.public.artist topic, and I'm just going to list from the beginning the first 10 messages. And I'll show the key, value, offsets, partitions, headers, timestamp, all of the information that's contained in each message. So I listed the first 10 messages. So the first thing you'll notice is they're not human readable. Now I could decode that. I'm gonna decode a file locally on my machine in a minute to show you what's contained in the message. Because we're using Avro is a binary format, and since I didn't use a decoder on this in a deserializer, they're still in the raw binary format. So that's why they look unreadable here. If I exit out of this container for a minute and let me go into my directory here, and I have a few files here. I've downloaded one of those files. So if you remember in S3, we had a series of Avro files, and I've just downloaded this first one ahead of time. So I have a copy of it from a previous run. I also have the Avro tools jar, and using that Avro tools jar, we can take a look at those Avro format files. Let me grab another command here. So first off, let's just see if you're familiar with the Avro tools jar, you can run a Java jar command from your command line, and I've pointed that at the Avro file that I downloaded. We'll see that, ignore the messages here. I don't have all the Hadoop libraries loaded locally. We don't need those. Again, 300. So there's 300 records or rows of information or data in this Avro file that represents 300 artists. And let's take a look at those. So I'll grab another command. This is using the same jar, and we're going to use the toJSON method, and I'm also using JQ. So Java jar, Avro tools jar, toJSON. I'm using the pretty flag. I'm just going to view the first 2 rows of data from this Avro file, and then I'm using JQ just to make it look nice on my screen. There we go. So again, up here when we are in the Kafka Connect container and I listed the messages in Kafka, they are in binary format. These are the exact same files. This is the Avro file that's in S3, and all I'm doing is viewing the first couple records. So you can see we have an artist ID, that's a unique ID. We have the name, which is a string, the nationality, the gender, birth date, death date. Again, some of these could be null. This particular artist that we've chosen here, the first one, has all of those fields. That's not necessarily true. The other thing that I've done, and let me switch over for a minute and I'll show you how that happened. If you're familiar with Debezium, the Debezium schema, there's quite a bit of information that comes over in the Debezium schema. I'm only focused on a few key fields for this demonstration. So let me open our Kafka Connect source connector first. Let's close this up and make a little room. So this is our source connector that we ran. I've changed the username and password here. This connector does a few things. This is the source connector that connects to our RDS database. I have the port information. Again, username and password I've changed here just for security. As you can see, I have the database name. So there is a database. Again, if we look over here, I've connected to that Postgres RDS database in PyCharm, and you can see here that there is a MoMA database. There is a public schema with 2 tables, artists and artwork. And again, we're only focusing on the artist tables. So artist ID, name, nationality, gender, birth date, and death date, which are the fields that you saw here in the messages that I viewed. Again, we're only focused on the public artist table. I could have done a list of tables. I could have used an entire schema. We're only going to focus on the public schema artist table. I'm using the AppRecura registry Avro converter. I've given it the address of my AppRecura registry. We're going to flip over there in a minute and take a look at our schemas that should have been written there. Basic configuration, you can find all this information in the AppRecura registry and Debezium documentation. One key thing here, so I'm doing a transform, I'm doing an unwrap. So I'm taking what is a large amount of information or data. If you work with Debezium, a lot of fields there can be useful for different workflows. I only need a couple of those rows for this demonstration. So first thing I'm doing is flattening the schema or unwrapping it. Only going to get certain fields. So we're going to get the source, the artist ID, name, nationality, gender, birthday, and death date. I'm getting the timestamp, the LSN, and then just grabbing the database table and schema. We don't really need that, but it's nice to keep that with the message so you know where it came from. So again, these fields here, if we look here, those are the fields that we see when I look at each Avro message. So instead of seeing 20 or 30 or more fields that are in the Debezium message, I've flattened that. I've done a transform to flatten it, and then by being explicit in the fields I want, I've excluded certain fields that I don't need for this particular case. One last field I'll call out here is the deleted. So this is not a particular artist that's been deleted. There's data in it. If this were a tombstone record in Kafka, if this were a Debezium delete, these fields would be null and this delete would be true. And that's going to help us to determine when we do a delete record, we'll be able to pick up on that delete record and make sure that that shows up as a delete in Hudi. That is our source connector. That's how we got the information into our Kafka topic and also into our data lake. If you recall, let me flip back to our diagram here for a minute. You recall our diagram. So what we did is by deploying our source connector and our sync connector and having Kafka Connect running, those source and sync connectors use some Confluent dependencies to write data to S3. It used Debezium to extract the data from Postgres and write it to Kafka. So this process, and you recall this was referred to as change data capture, that process is complete. So we've picked up all the original changes. Now we haven't done any changes to Postgres yet, but all the original changes have been picked up, written to Kafka, and the sync connector picked those up from Kafka and wrote those to S3. One last thing before we get into Hudi is AppRecura registry. So recall there was no artifacts here. Hopefully we'll see 2 artifacts now. So if you're familiar with Kafka, Kafka messages have a key and a value. We're not really interested in the key. That's not really meaningful to us, but what is meaningful is the value schema. Let me flip over to the content. Avro schemas are JSON, so we can look at the Avro schema. So this is the schema of our messages. Avro messages that were written to Kafka, Avro files that were into S3 are both based on this schema. And you can, as you look down here and you see database, table name, LSN, source timestamp, whether or not it was deleted, death field, birth date, this should all look familiar. So this looks exactly like our records in Kafka. Again, they're binary, so it's hard to tell. But if we decode one of our Avro files, and I've done that here from the command line using the Avro tools jar, we can see that, yes, in fact, that is the schema of each message. So if I slide this over, this is the schema, that is the structure of the messages. So these are the messages that are going to end up in S3, and these are the messages that Hudi's going to pick up. Okay, so far we've completed our change data capture. We're going to do some changes to the database in a minute, but now I'm going to demonstrate Apache Hudi. So now that we've completed the change data capture process, and again, that's still running. If we were to make changes right now to our Postgres database, those changes would be picked up, and we're going to see that in a few minutes. Those changes would be picked up by the source connector, moved into Kafka. The sync connector would then automatically pick those up and move those into S3, into the raw area of our data lake. So the change data capture process is running, Kafka connector is running. We're going to leave that running as part of this demonstration. What we're going to move on to now is the Hudi portion of the demonstration, specifically using Hudi DeltaStreamer. Information on Hudi DeltaStreamer can be found on the Hudi website, hudi.apache.org. One thing to call out, currently I'm using EMR version 6.4.0. That version currently uses 0.8.0 of Apache Hudi. Apache Hudi currently is at 0.9.0. For this demonstration, again, we're using EMR. EMR, the latest version of EMR, uses 0.8.0 at the time of this post. That's not a problem. All the features that we need will work just fine in that version. So if you're watching this demonstration and referring back to the documentation, make sure you're looking at 0.8.0. And if you're using the current version of EMR, that's the versions you want to look at. We're going to specifically be using DeltaStreamer, and you can see here that the Hudi DeltaStreamer utility, which is part of the Hudi Utilities bundle jar, and we'll be calling that jar as part of our Spark job, provides a way to ingest from different sources, such as a file store or Kafka, with certain capabilities. Let me flip back over to our diagram here. What's going to happen is we're going to, on EMR running Spark, again it's a Spark job, we're going to submit a Spark job which calls Hudi DeltaStreamer. We have some configuration files again that are loaded into our S3 bucket. Those are going to be pulled in, and I'll show you what those properties are in a moment and what the job looks like. DeltaStreamer is pointed to our Amazon S3 bucket where our Avro files were moved into the bucket by the CDC process. We're going to run DeltaStreamer in a continuous mode. There's a couple of different ways to run DeltaStreamer. We could just run it once. It would fire up. It would pick up any files, any changes. In this case, we're going to move those to a different location in S3, and then it would shut down. The other option, which we're going to use, is continuous. So once I start the job, it's going to run continuously, very similar to a Spark structured streaming job. There are some other options. There's also an option to use S3 notifications. DeltaStreamer would start up and run. It would shut down, and then every time it gets a notification that there is a new file that has been created and uploaded into the Amazon S3 bucket into that specific area, it would start up, it would process that file and then shut back down, so you're not continuously using resources. For demonstration purposes only, I'm going to fire up DeltaStreamer. I'm going to use a continuous mode, which I'll show you that flag in a minute, and it's just going to run in the background so we can see changes coming through. So again, with DeltaStreamer, we're going to move any files that come into topics, MoMA, public, artists, partition 0, key path or directory in S3. Again, we have 51 to start with. As we do more changes, we'll get more files in here as we make changes to our RDS database. DeltaStreamer will pick up those files and it will move them into Amazon S3 into Parquet format. And once we move those files, I'll show you what they look like. So flipping back over, I already have the command written, Spark submit command that we're going to run, so it's a Spark job. I need to point to two jars, so I need to use the Spark Avro jar because this is Avro format data that we're going to be reading in, and Hudi also uses Avro, and the Hudi utilities bundle. So you'll recall in the documentation specifically about Apache Hudi, it's part of the Hudi's utility bundle. So therefore we need to call that bundle. Again, there's no version number on this. This is going to be 0.8.0. Pretty basic command. Hudi has two different methods of writing. It has copy on write and merge on read. We're going to be using merge on read for our demonstration. You can read a little bit more about the two types of tables. So again, copy on write or merge on read. We're going to be using merge on read for this. Pretty basic Hudi configurations in this command. The source ordering field, we're going to use a timestamp field. The property files, I'll show you those property files in a minute. I have those loaded into S3, into the S3 data lake bucket in a separate location. I also have the target. So DeltaStreamer will read in the Avro files, we'll convert those to Parquet. It will do all its Hudi magic, and it's going to put those into a directory MoMA/artist/artist. Also, I mentioned we're using Apache Hive. In addition to writing the physical files, the Parquet files to S3, it's also going to create a Hive database and a table, actually more than one table, and I'll show you what those are in a moment. Once we get the process started, we'll be able to query the data that Hudi has written, and it will keep up with the changes, any inserts, updates, deletes, upserts. Hudi will manage all those changes for us, and then we'll be able to query the Hive metastore, the Hive database, and therefore the underlying data. And depending on how we query that, we'll get back all the records, or we'll only get back the latest records, which is what we're really interested in, because as a data scientist and I query the data, I want to make sure that the data I'm looking at reflects any changes that have been made in the Postgres database, the system of records. So as I insert new records, as I modify records, as I delete records, I want to make sure that my data scientists that are using the data lake data, that they're seeing the absolute latest data as reflected in the source database, the PostgreSQL database, and Hudi will take care of all that for us. A few other commands, so you can see continuous. I mentioned continuous. If we remove that flag, this job would just run once. It would process any existing data and it would shut down. And a few different options. We're going to use upserts. So we're just going to let this run. The initial kind of bulk of the Avro data are all just inserts, right? That's all the initial data that's in the table, the 15,000 artists. But then as we make changes, as we do inserts, updates, and deletes, this job will continue to run and it will continue to process those. Also, just a quick look, I mentioned the configuration file. So we have the base configuration file, configures some basic configuration about parallelism for Apache Hudi. And then I have a DeltaStreamer S3 properties file, which is specific to location of different resources, the schemas, file size, how I want the data partitioned. I'm going to partition it by nationality. Also the Hive database that I want to sync to and the table that I want to sync to. What the record key is, which is going to be the artist ID. Again, artist ID is unique, so it's going to be my record key, partitioning on nationality, just setting some different configuration here to make sure that the partitions, the Parquet files are partitioned and those match up with my Hive database. So as I query Hive, there's a one-to-one correlation between the partitions that have been stored in Hive and the actual partitions in S3 that contain the Parquet data. So we're going to go ahead and run our DeltaStreamer job as a Spark job, and again we're going to submit that directly from the EMR master node. I'm going to copy this command that we already went over to my clipboard. One thing before I start this command, I showed you the S3 bucket with the Avro data in the topics directory. I showed you the Kafka topics with the messages in an Avro format. I also just want to show you before we start, I mentioned we're going to be using Hive. I just want to show you that currently there is no MoMA database. So once we run this, the first thing that DeltaStreamer will do, because there is no database, it'll create that. So we show databases. If you're familiar with Hive, you can see we just have a default database, so we don't have a MoMA database. We'll flip back and we'll take a look at Hive from our notebook once we're all done. There will be a MoMA database which will be kept in sync. So as Hudi writes Parquet files using DeltaStreamer, DeltaStreamer will also keep the Hive metastore, the Hive database in sync, which contains the metadata and schema information about the Parquet files. And when we write our SQL queries and we do perform analysis against our data, which Hudi has written and managed, we will write those queries against the Hive database. So this is our command again. We went through the different commands. I showed you the configuration file for this. So we're going to start this up. Hopefully this will start up. Hopefully this will not fail, and hopefully this will continue running. So we'll give it a minute to start up. What's going to happen when I start this up the first time, because we already have got these 15,000 artists that it's going to process. It's going to put those into Hudi format, into Parquet. It's going to write those to a new location in our S3 bucket, which I'll show you if the DeltaStreamer starts up and runs properly. And then we're going to let it continue running. So again, our CDC process is running, DeltaStreamer process is running. Those processes are both running continuously. And then we'll make some changes to the database, and we'll also see those database changes come through. But let's first get our raw Avro data, which was put in our data lake by the CDC process, and get that managed by Hudi. We'll have Hudi convert that to Parquet and start managing that data, and then we'll start making some changes. So again, this is the DeltaStreamer command. I have logged into the master node of my EMR cluster. We could have also run this as an EMR step through the EMR UI or through the AWS CLI. We could have submitted this job. I'm just doing it in here so we can kind of watch the logs for the sake of demonstration purposes only. So the Spark job is running. DeltaStreamer is hopefully processing all those files that we saw, the Avro files. It is creating its logs. It's creating several different files that it needs to keep track of all these, and it is writing those files into a new location in our data lake, into a MoMA key path or MoMA directory, artist subpath. And then again, if you recall, we are partitioning the data by nationality. I showed you the DeltaStreamer properties, and if you recall the partitioning configuration specifically, it was by nationality. There's about 123 nationalities across the 15,000 artists. So I would expect to see in S3, when this is done, a MoMA directory, an artist subdirectory, and at least 123 subdirectories within that, one for each nationality. And then within each one of those subdirectories, Algerian, American, Canadian, we'll see Parquet files, one or more Parquet files, which represents the artists that are of that nationality. Now, the other property that we set as part of DeltaStreamer was the optimal Parquet file size, which was 128 megabytes. Since we don't have that many artists and the records are pretty small, I would not expect to see more than one Parquet file. Had I not set that, we'd probably see a couple small Parquet files, but since we've indicated that we optimally want 128 megabytes, it's probably just going to write all of the artists into one file. And then we'll go ahead and take a look at one of those files once DeltaStreamer has completed writing its files. While this is running, if I flip over, we'll come back out to our S3 bucket. We can in fact see now that there is a MoMA directory. There's also, Hudi also has a folder where it's keeping track of its progress. We have the MoMA directory. So we had the Hudi directory, which is where our DeltaStreamer configuration was. We had the topics directory, which the change data capture process, specifically log-based CDC process, Debezium, along with the Confluent dependencies, the source and sync connector, took that information out of Postgres, used Kafka as an intermediary, and then wrote those Avro files into a topic, the artist topic. And then Hudi, specifically DeltaStreamer, submitted as part of a Spark job, is processing that Avro data and writing that into Parquet. And this is the data that we're going to be analyzing, that our data scientists and data engineers, our data analysts are going to be writing queries against. So if we open this up, I'll just give you a sneak peek, and then in our notebook we'll take a little bit deeper look at what's in here. Hudi has a lot of configuration files. You can read a little more about Hudi and what the different files are and the purpose of these files. What we're specifically focused on, and again, remember, I'm showing you S3. Typically you wouldn't be going into S3, right? That's your data store. Your data is stored there. You're using Spark, Presto, Hive, different analytics engines to query that data using the metastore, AWS Glue, Apache Hive, right? You're not going into these files. Typically somebody wouldn't be going into here. So it really doesn't matter how many files are in here, how many files Hudi manages. Really the S3 bucket is, to think of it as just a data store, right? It's not something you're going into. You should never manipulate these files. Specifically, this MoMA directory is being managed by Hudi. I won't make any changes in it. I'm going to trust Hudi to manage all these files for me. So you can see here as we go in, we have, in this case, I've gone into the British nationality. So hopefully this Parquet file represents all the British artists. If you're familiar with S3, there is a query with S3 select. Now we couldn't look at the Avro data. We can look at Parquet data. So this is a handy feature. We can just use that command, go right into the S3 bucket and just take a look at this file, get a little preview of what this file looks like. Again, I previewed the Parquet file that was in the British nationality partition, right? So these are partitions, partition by nationality. This is the British nationality, so this should represent all the British artists. And I've previewed that file, again, using the query with S3 select, just to give you a sense for what's in here. And you can see that it looks pretty similar, right? So we have the artist ID, the name, nationality, which we see British, so we know it's working. Gender, birth year. We don't see death year. That's because this artist is most likely probably still alive. So the death year was null. Therefore, it didn't write it. That's something you should be aware of, right? So you can see here there is a death year. This artist was deceased in 1946. We also knew their gender. In other cases, we may or may not have all the fields if they were null. The rest of these fields should look the same, right? We have deleted, the timestamp, the LSN, the database table and schema. That was all part of the schema, which I showed you when we looked at the Avro file and was part of the Apache Avro schema that was written to Apache Registry. We can see that that's still running. The other things that you see added, so we have a few new fields. Hudi adds its own fields to each record. So we have the Hudi commit time, the sequence number, the record key, partition path, again, nationality is British, and the Hudi file name, so the name of this Parquet file. So in addition to the existing fields, which the schema defined and are part of each message, Hudi has also injected 5 more fields. So each one of these messages will have the existing set of fields. This part of the record came from Postgres. These were added on by Debezium, and again, I trimmed that list down and was very explicit about the fields that I wanted added. I dropped some fields that we don't need for the demonstration that Debezium would have normally added. Also, we flattened this out, right? So this is a flat JSON representation versus a nested representation, a lot easier to write queries against. So again, these are Debezium fields. These are from Postgres, and then Hudi added on 5 additional fields. So still a pretty small record, a few different sources for these fields. They'll all be of use, especially the Hudi when we start getting into different types of queries. We can see that our process is still running. The Hudi DeltaStreamer's process is running. Hopefully nothing will stop that or break that. That'll run continuously because we use a continuous flag. If I go back into my Kafka container just for a minute to show you that the CDC process is still running, we'll just confirm that our CDC process, so Kafka Connect with our source and sync connector is still running. I'll just take a look here and we can see in fact that it is. So this is our Kafka Connect, the Java process is still running. So if we go back over to our diagram for a minute, change data capture, log-based change data capture, Kafka Connect, this is running. This is running in a Kubernetes container on Amazon EKS. On Amazon EMR, we're running Hudi DeltaStreamer, which is moving the raw Avro data. When I say raw, it's untransformed, right? We haven't done a lot of ETL to it. That raw data that kind of represents the records that were in Postgres. DeltaStreamer is taking those files. It's processing those. We could do some additional transforms if we wanted. It's pretty powerful. DeltaStreamer using a very basic implementation of it. And we're writing that file into Parquet, and we took a look at those records. So everything is working as expected. I'm going to switch over to my notebook now. So this is a notebook. It's part of the code on GitHub. We're going to walk through these fields. So just some informational background. I'm going to skip through these. We already know this, right? The moment database. We started our Hudi DeltaStreamer job. I've started the Spark session just because it takes a minute to start up. Nothing special, just a PySpark notebooks, Spark Magic notebooks. We're just running a Jupyter notebook here. I've started a Spark session, nothing special. I do have some configuration here. AWS has some good documentation on using Hudi with EMR. There's just a few basic configuration items that you need to be aware of and configure when you're using Hudi. It talks about it in the documentation. There's a Hudi section of EMR. Just read through those. Some basic configuration you'll want to be aware of. So I've ran that configuration, added to my Spark session. Pretty minimal imports. This is pretty big. We're going to use Spark SQL. So if you're familiar with Spark Magic, I could also run Spark Magic commands. So I could do something like SQL, and then I could just start writing, select star from. We could use that format, or we can use a spark.sql and write our SQL commands just for the sake of simplicity and consistency. And either one of these will work just fine. I'm going to use the spark.sql versus using Spark Magic. So first off, you remember that when we were in EMR back here before I started the process running, I showed you that there was just the default Hive database. So let's run this. We're using Apache Hive. I've installed Apache Hive on EMR. I should have pointed that out ahead of time. You can see here that the default database, so that's the default database that's part of Apache Hive when you install it on EMR. But we now have a moment database, which we didn't have before. The Spark job, which is running Debezium and specifically DeltaStreamer, the first time that it ran, it saw that there was no moment database. It created it. It's also hopefully created 2 tables. You probably would have expected a moment database artist table. In fact, there is, but they have 2 suffixes. So there's artist_ro and artist_rt. If you want to find out more information specifically about these files, so you mentioned you remember I mentioned there's a copy on write and a merge on read. It talks a little bit about these tables in here and what they mean. So Hudi creates 2 tables in the Hive metastore for merge on read. So again, merge on read, that's the particular table type we're using for this demonstration. I could have used copy on write, but I'm using merge on read. A table with the name that you specified, which is the read optimized view. So if you're familiar with Hudi, there's a few different views of the data that we can get. With merge on read, we get a read optimized view. So again, that's the RO table, so read optimized. And then again, I'm back in the Hudi documentation for RT. You can also see that table with the same name appended with RT, which is the real-time view. You can query both tables. So when you write your queries, perform your analytics using Hudi managed tables, so these are Hudi tables. These are synced with Hive. We're going to query Hive. These reflect the underlying data that Hudi is managing in S3. We can query the read optimized view, or we can query the real-time view of the data. So the read optimized view is going to be the existing data before any compaction. The real-time view is going to be right up to date. So if we do an insert, update, or delete, those should be reflected. So if we delete a record, we should in fact not see that record. If we modify a record, we should in fact see the modification versus seeing the original file before compaction, or seeing both files, both the original and the alteration. If you want parity between what the data analyst sees in the data lake and Postgres, then hopefully as I query data in Postgres, I would get those same results if I query it in my data lake, and we're able to do that because of Hudi. So again, those are the two tables. Run another command here. So let's just take a look at that table. I use a describe, basic SQL describe statement. We'll describe the read only. You can see here. So we see the Hudi columns, our PostgreSQL representing the original artist database columns, and then we see the Debezium columns, which I called out. We recall that the information in S3 again was partitioned, right? So we saw the approximately 123 nationalities, or 123 partitions representing each nationality. Since we've synced Hudi Parquet files that it's writing, that same information should be synced with Apache Hive. In fact, here if I show partitions, we could also pick the real-time table. I'm just showing the first 15 partitions. We in fact see those exact same partitions here. Let's just take a look at a couple records. I'll just do a simple select star. We'll just switch this. We'll use the real-time table. It won't really matter right now. And we'll just show the first 5 records. And ideally, they're going to look just like they did when we looked at the British Parquet file represented as JSON. And I would expect to see the exact same thing when I query the first 5 records here. It's going to look very similar. So we have parity between Postgres, Kafka topic, Avro files in S3, and now Parquet files in S3. And there's the parity obviously between those. So the information has been successfully moved from Postgres to Kafka, to S3 and Avro, to Parquet, and we've maintained the record integrity, the data integrity of those records. So here we see the first 5 records. Again, same fields, right? So we looked at describe the table here, the schema. Here we see the column names, and we see the first 5 records, which happen to be, looks like the Belgian artist of Belgian nationality. I mentioned the files in S3. We took a look at those when I flipped over to S3. We could also run the same command. So I'm little Spark magic here. I'm using the Spark magic to write a shell command. I have my data lake bucket, and I'm just running an AWS S3 API list objects v2 on that bucket. I'm saying just show me the first 50 items in the bucket, recursively showing me the contents and the key path. So here's the basically first 50 files, and you can see that Hudi has a number of configuration files that it maintains, different commits, in flight, requested, any compaction. And then as we move down a little bit, we see here, starting here with nationality with Afghan, Albanian, Algerian, American, we start seeing each one of our partitions. There's this .hudi partition metadata file, and then we have 1 or more Parquet files. Now right now we only have 1 Parquet file per partition, again because we optimize those for 128 megabyte, and given such a small data set, none of the files are that big. But as we write some changes, we'll see that change. So the next step, we want to make some changes to our database. So we're going to make some changes, and I would expect to see those changes picked up by our change data capture process. The changes in the Postgres database will be picked up, and using Apache Kafka as an intermediary between our Kafka Connect source and sync connectors, we'll move that data as Apache Avro files into Amazon S3. Our DeltaStreamer, which is still running, will pick up those changes in the raw part of our data lake in Apache Avro format, and it will manage those changes, write those to Apache Parquet, And then we should be able to query those changes and take a look at the different types of queries we can use with Apache Hudi. So a little bit of background, if you recall from the documentation earlier on, we looked at the different table types. We created our MoMA, Apache Hive MoMA database, which was created when DeltaStreamer started for the first time. It created the database. You'll also recall that we talked about the two tables, the artist_ro and the artist_rt tables. You recall if we looked at the documentation, and I took this little blurb from the documentation. So from the AWS documentation, Hudi creates two tables in the Hive metastore, a table with the name you specified, which will be the read optimized view. So it'll have the _ro, so artist_ro, and a table in the same path appended with _rt, which is the real-time view. And you can query both tables. So we have the artist_ro and the artist_rt. We're going to make some changes. We're going to make 2 upserts and 1 delete to our database. And then we're going to look to see how those changes are reflected with Apache Hudi, and we're going to run some queries against those. So I'm going to switch back over to PyCharm. Now, I've already set up a few changes here just to save us a little time. So I have an upsert. I'm going to take artist445, and let's assume that the dates that we had were wrong. So we're going to change the birth date from 1879 to 1881, and we're going to also update the year of death from 1961 to 1962. In addition, for artist 535, we did not know the year of birth or the year of death for that particular artist. Let's say that we researched that and found out that it was 1900, and they passed away in 1981. We're going to also make a change to artist 535. So artist 445 and 535, we're going to modify both those records. We should see an upsert of those records into Apache Hudi, and when we query those, we should see the latest changes reflected. So we'll go back and remind ourselves what those changes were. So let's go ahead and run those. I'll just run these 2 update statements, and I'm going to run these against our database. And when I'm done running them, I'm going to quickly switch back over. This is, if you remember, Hudi DeltaStreamer is running as a Spark job. You can kind of see that typical log output. And then we should see some changes. We'll see how quick it can pick up the change that we do. So go ahead and execute that and flip back quickly. You can see that almost instantaneously those changes were picked up. Now, what's more amazing about that is that keep in mind that that means that the change was picked up, the change was made to PostgreSQL, the change was written to the logs, Kafka Connect source connector picked up those changes in the write-ahead logs using log-based change data capture with Debezium. Those changes were written to Kafka. The Kafka Connect sync connector then picked up those changes in the Kafka topic and wrote those in Avro format to Amazon S3. At that point, Apache Hudi, the DeltaStreamer Spark job that you see running on my screen, picked up those new Avro files and then wrote those in Apache Parquet, wrote all the appropriate files and transaction logs to manage those changes, those upserts, into our data lake. So almost instantaneously, we saw those changes picked up. If we go back over to our notebook, I'm going to run a couple SQL queries to show you. So I've written one. If you recall, the 2 artists that we did our upserts for were 445 and 535. So I've written a simple select star from the _ro table and then the _rt table, where artist ID is in 445 or 535. So that should pick up both of those, and we'll see the read optimized view first, and then we'll see the real-time view. So we'll go ahead and run both of those. They're going to take a minute. Now, you'll notice that these queries take a little bit of time. Keep in mind I have a very small cluster running for this demonstration just to save money. It's certainly not a production cluster. I also have Hudi DeltaStreamer running on the exact same cluster. So I have a small cluster. DeltaStreamer is running continuously, and at the same time I'm running queries, and these are fairly large queries. Again, they have 125, 123 partitions, but I'm doing a select star, so I'm not using those partitions. I'm not doing any predicate push down. I'm really doing a select star statement. It's going to take a few seconds to read that information in S3. So you can see that our read optimized query statement ran for 445 and 535. And we can see that we have both of those records returned. So before we take a look at those, let's let our query against our real-time table return so that we can compare and contrast or see if there's any differences. Okay, so those records returned. Let's take a look and see what we have. So for our read optimized view, Again, if you remember our changes, so the first one we went from 1879 to 1881, 1961 to 1962. We'll see that for the read-only table, the query, we see that none of those changes are reflected, right? You'll note here too by the operation, these are the original two records as denoted by the R in the operation, in the Debezium operation in the write-ahead log. That flag is picked up, and we see that these are the original inserts into that were picked up by Debezium, two reads. Those are written to Apache Hudi. Now you can see the difference here if you look at the same field, the underscore OP or operation field. We can see that both of those are updates. We see the two original reads that have been written to Hudi. Those were the existing records when the source connector started up and kicked off and just read all that data in, wrote it to Kafka, wrote it to S3, picked up by DeltaStreamer, written as Parquet. So those are the two original files. Now if we see the real time, we actually see the changes. So we see 1900 and 1981. We see 1881 and 1962. So those are the updated years. So that's the real-time view. Those are our two upserts. So next, let's do a delete. So I'm going to go back to PySpark. I've just randomly picked a record, and we're going to go ahead and do a delete on that. And again, I'm going to flip back over so we can see how fast that gets picked up. The CDC process is very fast, and DeltaStreamer is very fast. So as you make changes in your database in near real time, those changes are picked up and moved into the Hudi managed files and synced with Apache Hive, and they're queryable. So we'll go ahead and run that. Again, almost instantaneously, the Kafka Connect source and sync connectors, where we're working with our change data capture process, those changes were picked up. They were placed as Avro files in S3. Those changes were picked up by DeltaStreamer and moved into the Hudi managed Parquet files. So if we go back over to our notebook, I've written similar queries. So first we're going to look for, again, that was 451, artist ID 451. I've written two queries. First, the read optimized table, and then the real-time table. So we'll go ahead and run those queries, specifically this time looking for artist ID 451. And we'll let those finish, and we'll compare and contrast what we would expect to see in the read optimized table versus the real-time table. Okay, so both those queries finished. It took a minute, so I stopped the video and restarted it when they were complete. And we can see that, again, we deleted artist 451. We did a delete from artist 451. And we can see that when we did a select star from both the read optimized and the real-time tables, we got similar results back from Hive. One thing to understand about Apache Hudi, certain facets of Apache Hudi can be a little confusing at first. When you think about a delete in a database, right? If I delete a record in a database, it's gone. With Apache Hudi, there's two types of deletes. There's a soft delete and a hard delete. And you can read a little bit more in the documentation. So I'm in the 0.8.0 documentation. There's two different types of deletes. What we've done is a soft delete. There's also a hard delete. So with a soft delete, the record is retained, but all of the values are nulled out. And I'll show you that in a moment, which indicates a delete. Also, the operations flag becomes a D. So Debezium changes the flag to D. If you recall, Debezium has 4 flags. They're CRUD, right? So create, read, update, and delete. And it changes the operations flag to D for delete. The underscore deleted flag becomes true, and all of the records become null. And that'll be reflected in the query. The other way we can do that is a stronger form of a deletion. So if you physically have to remove a record, you don't want to leave any record of it, right? So oftentimes you may want a record that a field was deleted. So you want to do a soft delete. If you just want to get rid of it, so no matter what, the record's gone. Whenever you perform a query, there's no confusion. That record's been deleted. There's no trace of it. Then you would do a hard delete, and Hudi goes into 3 different ways to do that. For this demo, I've done a soft delete. So you'll notice here, we'll look at the real-time table, for example. We have we looked at 451. We see 2 records. First, we have the original read, right? So that was that bulk insert we did of the existing snapshot from PostgreSQL. So all of the existing 15,000 artists that were already in the table when we started the source connector, Debezium picked those up, and eventually those are written through CDC. That was the read flag. We have a second record, which is the D or delete flag. We also see that the deleted field has a value of true versus false, so it's now true. And then you'll note that the name, gender, birth year, death year, are all null. Another thing you'll notice, which is a little odd, and I think this is also can be confusing, you have to be a little careful with your queries. You'll notice that we partitioned on nationality. So instead of nationality becoming null, it actually became default. Artist 451 happened to be of the nationality Italian. When we deleted that record, it created the delete record, nulled everything out, but changed the partition to default. So we now have a new partition called default, which contains this record. I find it a little confusing, and I could foresee that causing some issues if you're not aware of that. But again, we can see the nationality is in fact default, so that partition is default. But the other fields have been removed. They're all null. Obviously, we need to keep the artist ID so we can identify the record, but all the other fields have been turned to null. And again, the operations flag is a D for delete, and the deleted field is now true. So that's how we show a soft delete of a record. Again, a little different from a hard delete. And once again, I would suggest reading up on deletes with Hudi and how they work. Again, you can do either a soft or a hard delete depending on what you need, and you need either or depending on your circumstances, and implement both depending on the type of data you're working with. But again, we did a soft delete. So that ends our demonstration. I hope that you learned a lot. I hope you know more now about the change data capture process that we went through. So we talked about change data capture, moving changes from a PostgreSQL database using a Kafka Connect into Amazon S3. And then we talked about Apache Hudi with DeltaStreamer, picking up those changes and writing those into Apache Parquet, and then making those available for our data analysts.